Hello there. In this video, I'll demonstrate how to calculate the number of failures per unit hour and the mean time between failures, or MTBF, along with the estimated number of breakdowns per year. The questions covered in this video correspond to problems 17.7 and 17.17 in your text. Let's start with problem 17.7. Here we have a manufacturer of touch screens for tablets, and they want an MTBF, or mean time between failures, of at least 50,000 hours. Recent test results for 10 units were one failure at 10,000 hours, another failure at 25,000 hours, and two more failures at 45,000 hours. The remaining units were still running at 60,000 hours. We have three requirements here. The first is to determine the percentage of failures, the second to determine the number of failures per unit hour, and third to determine the mean time between failures at this point in the testing, or MTBF. The calculation for the percentage of failures is really quite simple. It's equal to the number of failures divided by the number of units tested. In this case, we have 4 failures over 10 units tested for a total failure rate, or percentage of failures, of 40%. For requirement 2, the number of failures per unit hour. This is also known as FRN, and that's equal to the number of failures divided by the operating time. How we go about determining the operating time in the denominator is actually going to be based on the total number of units tested by the 60,000 hour full operating time less the non-operating time of all of the units that failed. With this question, it helps to draw a timeline to see when each unit failed. So we have 10 units that were put into testing for 60,000 hours. The first unit failed at 10,000 hours. Which means its operating time was 10,000 hours, and that its non-operating time was 50,000 hours. We had another unit fail at an operating time of 25,000 hours, which means its non-operating time was 35,000. Then we had 2 units fail after 45,000 hours of operating time, which means the non-operating time for those units were 15,000. So our calculation for FRN then is the number of failures 4 divided by 10 units times 60,000, which is the expected total operating time of all units put into testing, and then we subtract the sum of all of the non-operating times of the failed units. So first we'll subtract one unit with a non-operating time of 50,000 hours, then we'll subtract another unit with a non-operating time of 35,000 hours, and then subtract 2 units times a non-operating time of 15,000 hours. So that's 4 units divided by 485,000 hours. Which results in a pretty small number, 0.000008247 failures per unit hour. That's a really small number and somewhat meaningless when we look at it, which is why we have mean time between failures, or MTBF. The mean time between failures is equal to the reciprocal of the number of failures per unit hour, or 1 over FRN. So if we take 1 over the number we just calculated, the mean time between failures is 121,250 hours. That's a little bit more meaningful to understand than 0.000, etc. Now on to problem 1717. Here we have a fire department that has a number of failures with its oxygen masks and is evaluating the possibility of outsourcing preventative maintenance to the manufacturer. Now, because of the risk associated with the failure, the cost of each failure is estimated to be $2,000. Now, the current maintenance policy, where the station employees perform the maintenance, has the following history in terms of the number of breakdowns and the number of years in which breakdowns occurred. So what this table tells us is that there were 4 years where there were no breakdowns, 3 years where there was 1 breakdown, 1 year where there were 2 breakdowns, 5 years where there were 3, 5 years where there were 4 breakdowns, and there were no years that had 5 breakdowns. The manufacturer that's offering the outsourced service will guarantee repairs on any and all failures as part of a service contract at a cost of $5,000 per year. We have 3 requirements for this problem. First, to determine the expected number of breakdowns per year with station employees performing the maintenance. Second, to determine the cost of the current maintenance policy. And then third, to discuss which is the more economical policy. For requirement A, the estimated breakdowns per year, well, that's equal to the total number of breakdowns divided by the sum of all the years with breakdowns, where the total number of breakdowns is equal to the sum of the breakdowns times the number of years where breakdowns occurred, divided by the sum of the number of years with breakdowns. So we'll just cheat and use the information in our table. So 0 times 4 is 0, plus 1 times 3 is 3, etc., all the way to 5 times 0, 0. And when we add all those up, the total number of breakdowns is 40. And the sum of the number of years with breakdowns adds up to 18. The estimated number of breakdowns then is the total number of breakdowns divided by the number of years with breakdowns. So we'll take 40 breakdowns over 18 years with breakdowns. That results in 2.222 breakdowns per year. For requirement B, the cost of the current policy is $2,000 per failure times the estimated number of breakdowns, or 2.222, which results in an estimated cost of $4,444 per year under the current policy. For requirement C then, to determine which is the most economical, if the cost to outsource is $5,000 and the estimated cost of maintaining in-house is $4,444, well, that's a savings of $556 per year by performing the maintenance in-house. Therefore, the current policy is more economical than the outsourced option.